So now that we've established that this data set I collected very carefully, that there's some evidence it can be normally distributed, or that it is normally distributed, the next question is, based on that data set and the average and the standard deviation I calculated, what is the probability of finding someone whose hand span is less than 13 centimeters? So I did some numbers and I worked out these two quantities, and then I did a little work to show that there was evidence that the set was normally distributed, and I got some. What I'd really like to know is, if I were to walk into a room and pick one person at random, what's the probability that that person's hand, from their pinky to their thumb, is less than 13 centimeters? So if you recall from earlier in the video, everything about the normal distribution is based on how many standard deviations you are away from the average value. So that's what I'm going to think about for this particular data point. If I take 13, I want to find out how far away that is from the average, 15.3. So I'm going to find the difference, 13 minus 15.3. And if I work that out, (13 minus 15.3), I get negative 2.3. So it's negative because 13 is less than the average, so that's nice, it worked out that way. So I'm 2.3 centimeters shorter than the average value. Now, I want to know how many standard deviations that is, because that's going to tell me how far down my distribution I've traveled. So if I were to take this distance here and chop it up into units the size of one standard deviation, I'm just going to write that under both of these fractions here. I would get 2.3 divided by 2.22 is negative 1.04 if I round. So what that's telling me is that the data point 13 centimeters, is 1.04 standard deviations below because it's negative, the average value. Now, this quantity, the number of standard deviations I am below or above the average, is called a z-score. And this happens to be the z-score of the value 13. So within this data set, with an average of 15.3 and a standard deviation of 2.22, the z-score of a 13 centimeter hand span is negative 1.04, because 13 centimeter hand spans is 1.04 standard deviations below the average value. So what can I do with that? Well, if you were to go on to the page, which is where you found this video, you will find a link to something that looks like this. It's a standard normal probability table. And what it's doing is it's showing you the probability of any particular value being less than a certain z-score. So there is a video below this that will show you exactly how to use it. But if I were to check on this, if I were to find negative 1.04, I end up with a value of 0.1492. So the way you would write that is the probability of a z-score being less than negative 1.04 is, I have to look it up again, 0.1492. Which I believe is the year that Christopher Columbus sailed across the Atlantic Ocean in order to commit genocide of indigenous people. Fun number facts. But what this is telling you is that that person, 13 centimeters, their hand span being this many standard deviations below the average, you have only a 14.92% chance of the next person you meeting having a hand span less than that size. Not that size, less than that size. So the answer to this question, based on the data, what is the probability of finding someone whose hand span is less than 13 centimeters, is 14.92%. So the second type of question I could ask is, instead of less than a particular value, I could figure out what the probabilities of it being more than a particular value. So I said at the beginning, mine was 18 centimeters, and based on this average and this particular standard deviation, what is the probability of having someone whose hand is bigger than mine, more than 18 centimeters? So in order to find that, I have to figure out how many standard deviations this is above the average. So I'm going to need the z-score of 18 centimeters. To do that, I take the value of the data point and I subtract the average value to find out how far above it is. And then I chop that up into units of standard deviations. So that ends up being 18 minus 15.3 is 2.7. And 2.7 divided by 2.22 is 1.22 if I round. So this question, based on the data, what is the probability of finding someone whose hand span is more than 18 centimeters? I am after the probability that Z is greater than 1.22. Now, if you are adept at the internet, you can go on and you can find a chart that will give you greater than values. It's not really necessary. You only need a chart, you only need one. Either the one that gives you below or above, and then you just stick with that particular one. I'm going to ask sort of a related question. What is the probability of Z being less than that? Because that's the only thing my chart will tell me. Well, if I look that number up, 1.22 is 0.8888. That is a lot of 8s. If the probability of being under 18 centimeters is 0.8888, then the probability of being over 18 centimeters must be whatever's left. So if I were to take 100%, a 100% chance of finding someone with a hand, and subtracting from it the probability of them having less than this z-score, I would end up with the answer to how many of them have more than that z-score. You'll have to maybe let that roll around your brain a bit. 1 minus 0.8888 is 0.1112. So if I were to walk up to someone random on the street, based on the data I had collected with this average and this standard deviation, there's only an 11.12% chance that that person would have a hand span larger than mine. So, and here's the question that if you're a glove manufacturer, you're most concerned about. What is the probability of finding someone whose hand span is between 14 centimeters and 16 centimeters? I imagine that hands that fit between those two ranges could probably wear the same glove. It would be a little big on these people, a little small on those people, but they would fit. So I want to know what percentage of the human race, based on that data set I collected, could wear a glove that would fit in someone in this range. Like, what percentage of the people could wear that? If it's all of them, then I only have to make one size. If it's only 10% of people, then I'm going to have to make many sizes. So how do you do this? Well, I'm going to need the probabilities of being under this and the probabilities of under that. So I'm going to need z-scores of both of them. So the z-score of 14 would be 14 minus the average divided by the standard deviation. And that gives me 14 minus 15.3 is divided by 2.22, negative 0.59 if I round. And the z-score for 16 would be 16 minus 15.3 divided by 2.22. .32 if I round. So if I get out that chart again, I'm going to check the probability of finding a z-score less than negative 0.59. And I find 0.2776. And the probability of finding a z-score less than 0.32 0.6255. So if I were to quick sketch a normal distribution for you, something like so. The probability of being less than 0.32, a 0.32 z-score means you're 0.32 of a standard deviation. So one standard deviation is about there, 0.32 would be about here. So what I have in this is that 62.5% of all this space under here is less than a z-score of 0.32. Now that's not what I was asked. I was asked for the probability of it being between these two. So I'm going to fetch another color then. I'm going to find where negative 0.59 would be. If that's where my one standard deviation is, then 0.59 is probably here. Do you notice that this chunk is a piece of the larger chunk? So if I was trying to figure out what the probability was of being between these two bars, I would need the probability of being under this one, but subtract the probability of being under that one. I don't want the tail, I just want this piece between. So the probability of finding a z between negative 0.59 and 0.32 ends up being the probability of z being less than 0.32, subtract the probability of z being less than negative 0.59. Well, I already have this number. It's 0.6255. And I already have this one. It's 0.2776. For a final value of 6255 minus 2776, I get 0.3479. So that's a 34.79% chance. Which means that based on that data set that I had collected, you could expect 34, almost 35% of human beings to have a hand span between 14 centimeters and 16 centimeters. So if you think about symmetry, there's 35% there, then the remaining is split into two categories. You have large gloves, medium gloves, small gloves. And you can bet your bottom dollar that there are people being paid lots of money to study the size of people's hands, the length of people's arms from shoulder to wrist, the people measuring from hips to ankles, in order to figure out just how big a typical person is and what percentage of people could wear pants that are 34 inches long, or what percentage of them need between 34 and 36, and what percentage need between 36 and 38. And then you can go to a store, whichever your favorite clothier is, and go dig through the piles of clothing. And you'll notice that if a store just buys 10 pairs of each size, that after about a week, there are so many extra large pairs of pants left that's all there is in the bin, and you can't find your size anymore. But a clever retailer would buy 10 of the mediums, 5 of the large, 2 of the extra large, 1 of the extra large, because these percentages of people, based on data, will require that particular size. This discipline is called actuarial science, and it pays very well if you can get through the program at university. So something to consider. So since everything here is based on an average and a standard deviation and the presumption that you can model the data with a normal distribution, we're going to use some symbols in order to render all that information so we don't have to keep writing the same 15-word sentence all the time. So if I want to tell you that a particular feature is normally distributed, I would say X, meaning the data in question, follows or can be approximated by a normal distribution. Now once I've done that, the two pieces of information I need to have are the average value and then the standard deviation. So if I were to phrase a question like this for you, given that the data points can be modeled by a normal distribution with an average of 8 and a standard deviation of 2, what is the probability, so calculate, the probability of any particular data point being less than 5. Alright, so first off, if I have this, I'm being asked to find where in this distribution a 5 would be located, so I need to determine how many standard deviations away I am. So I'm going to need the z-score. So the z-score of 5 is take the data point in question, subtract the average. You can tell it's the average because it's quoted first in this bracket, and divide by the standard deviation, which was handed here to you in this as the second number in that bracket. 5 minus 8 is minus 3. So I'm hunting for a z-score of negative 1.5. So this question here, the probability that any given data point is less than 5, is the same as asking what the probability is of finding a z-score less than negative 1.5. These are equivalent based on these two numbers. So if I go and I look at this particular chart, negative 1.5, I get a value of 0.0668. So therefore, the probability of finding anything less than 5 is 0.0668, which is a 6.68% chance. So these questions are really quite quick once you get the hang of using the chart. And again, there is a chart for you to download on the page just below this video. And just below that is another video I borrowed from the interweb to explain to you how to use it in gross detail. So there's something for you to think about. Now, you'll maybe notice that when we were doing the z-scores, we kept repeating the same calculation with the same bits over and over and over again, which means there's a formula for this. So I'm going to render it that way for you. The z-score of any particular data point is take the data point, subtract the average, and divide it by the standard deviation. Now, you've seen that before. You did this back in the single variable analysis unit. So that's what this z-score was doing, was finding the location of a particular data point within the distribution of the data. And then now that we've done this and assumed that it's a normal distribution, we can use that location or address within the distribution to work out some probabilities.